Well, hello there. Today we are talking about centripetal force. Now, when I was a kid and I looked at these roller coasters that looked like this, I don't know about you, but I looked at one of these loop-de-loops and I looked at the car that went on the loop-de-loop like this, and I said, I don't understand how the people who are in this car don't fall out when they're upside down. That didn't make any sense to me. I said, somehow if you're going in a circle, you don't fall out, but then if you're just sitting still, you do fall out. What does moving have to do with whether or not you fall out? Well, that's what we're talking about today, is this concept of centripetal force and why when you go around a roller coaster, you don't fall out at the top. That's our main topic of the day. Now, we're going to start with, in order to understand the concept of centripetal force, you have to understand the concept of centripetal acceleration, which is what we talked about last time. We say that if you're going in a circle, you are accelerating, because if you're going in a circle, you're changing your direction the whole way around, and changing your direction is changing your velocity. Wow, unused printers. That's exciting. Changing your direction is changing your velocity, so anytime that you're going in a circle, you are accelerating. Well, we know from Newton's second law that if you're accelerating, you gotta have a force. If I were to take something like this rubber stopper here, which I thought was attached to the string, but then unfortunately was not attached to the string at the end of the day, so that is really super unfortunate. But let's see if we can make it be attached to the string. We maybe can, we maybe can't. TBD. I think we got it. I think it's about to happen. 1 second. Okay. Stay. Okay. Suppose that I have this rubber stopper attached to a string like this. If I wheel it around my head, it takes a force to keep it going in a circle. I know that it takes a force because there's tension in the string, and that tension is creating a force on the rubber stopper. A centripetal force is any type of force that makes an object go in a circle. That's what a centripetal force is. I'll say that definition one more time. It's any force that causes an object to go in a circle. Centripetal force is any force that causes an object to go in a circle. A centripetal force could be really any type of force. For this rubber stopper, it's the string. The tension in the string is acting as a centripetal force to pull it in a circle. For we just have a lot of different notifications. For planets that are orbiting around the sun, gravity is the centripetal force. Gravity is what makes them go in a circle. For cars that are traveling on a road, the force that makes a car travel on a road and it goes in a circle, what allows it to go in a circle is friction between the tires in the road. So for all of these different examples, all of these different things can act as centripetal forces. Any type of force can be a centripetal force as long as its purpose is to make an object go in a circle. Now we know from last time, or I should start here. We know from Newton's second law that force is equal to mass times acceleration. And if it's a centripetal force, then that centripetal force is equal to mass times centripetal acceleration. And we know from last time that centripetal acceleration is VT, that tangential speed squared over R. And so you multiply that by M and you get an equation for centripetal force, that is mv squared over R. Now this equation you can absolutely add to your bag of tricks, or you can just derive it each time knowing that it just comes from Newton's second law and you already have an equation for the centripetal acceleration. Let's talk a little bit about how this centripetal force works and what the centripetal force looks like. Suppose that I was in a car driving down the road and I look over to my left and I see an ice cream shop. Now, something you should know about me is that I do love ice cream, like very, very seriously. It is one of my favorite desserts of all time. One of my great passions, you might say, is ice cream. I just love ice cream. I love every flavor of ice cream. I'm always looking for ice cream. So suppose that I'm driving this way. And we'll take a little bird's eye view of my car here. So here's the top of my car. It's going this way down the road. And I see a little ice cream shop out here to my left. That's an ice cream cone, obviously. And suppose that I'm going this way. And let's say that I have a passenger in the car with me. So here's me. I'm sitting in the driver's seat. And here is the passenger who is sitting next to me in the car. As I'm driving forward this way, Then, all of a sudden, I decide that I would like to take a quick turn. And so I turn the car so that now I'm headed straight towards that ice cream shop. Here's me, here's my passenger. And now we're going this way, and that's the new direction of our velocity. Wow, what just happened with that vector hat? I don't even know how that happened. Oh, I see. Okay. Okay, this is the direction of our velocity now. Now, here is my question for you. Do I have mass? Does my passenger have mass? You say, yes, Miss Wilson. What's the point? If we have mass, then we have inertia. Now, first, we had inertia going this way and inertia going this way. And I say inertia going that way. Of course, it's not really going that way. If we wanted to be more specific, we would say that our momentum was going that way. But we had inertia, and we were an object in motion that would like to stay in motion. So our bodies, which were moving this way, would like to keep on moving that way. And so we try to keep on moving this way. But then you turn the car. So now the car is going this way. And check it out. This passenger here who would like to keep going this way, now there's a wall. There's the car door in the way of where the passenger wanted to keep going. That car door acts as a force to push them so that they go in a circle. The harder I turn, the harder they'll feel themselves being slammed up against the car door. Now let's be very clear here about what's going on. A lot of people will talk about this situation, and they'll talk about something called a centrifugal force or a centrifugal force. Centrifugal force. And they say the centrifugal force is this force that you feel that pulls you towards the car's door. So as you're sitting there, you feel this pull all of a sudden towards the car door, and we call that the centrifugal force. Here's the truth, is that the centrifugal force is a fictitious force. It's the feeling of getting shoved up against the wall. But what's shoving you up against the car door is not the centrifugal force at all. It's really your inertia. There is no force that shoves you up against the wall. What shoves you up against the wall is your body's tendency to keep doing what it was doing. It was going in a straight line in constant speed, and it wants to keep on going in that straight line at that constant speed. And so your body will try to keep doing what it was doing, and the car will turn instead. So the centrifugal force is not a real force. That feeling that, I really, my body is trying to keep on doing what it's doing, it's slamming up against the wall. There is no force that's slamming you up against the wall. It's just that your inertia is slamming you up against the wall. Here's the actual force that's happening. Most forces, with the exception of things like gravity, most forces are not things that you actually, feel happening to you without some sort of contact. Most of the forces that you experience in your daily life are contact forces. And so what the forces that you actually experience, the only force that you really actually experience here is the car door. Wow, what just happened? We just got crazy. Let's change our color so that you can see it in a different color. The only force that you're actually experiencing here is the car door pushing back against you, keeping you from going the way that your inertia would have you go. Your inertia would have you go this way, but the car door pushes back against you. For that reason, the car door acts as a centripetal force. The reason why the car door acts as a centripetal force is because your inertia would want you to keep going in a straight line, but because there's a car door there, you don't go in a straight line. Instead, you actually do make the turn and head towards the ice cream shop. Now, let's take a look at another example. In class, I take a giant bucket of water and I swing that bucket of water over my head. And you've seen this trick before. It's a very nice party trick, one that you can pull out at any sort of party that you would like to, and it is a sure guarantee to impress all of your friends. But here's the question is, if I spin a bucket of water in a circle, why doesn't the water fall out at the top of the circle? And this really goes back to the roller coaster question of my childhood. I need to redraw this whole situation. One moment, please. This really goes back to the roller coaster question of my childhood, which is, why did the people not fall out when they ride the roller coaster and go up to the top and they're hanging upside down? Why don't they fall out of there? And there's a reason for that. Here's the idea. That's it. I just can't draw a straight line. It's really obnoxious. I'm just really trying. Okay, let's see. Here we go. And then... Come on. I did it in a bad spot. Okay, let me try one more time. Oh, hey, actually, team, 1 second. I just realized I need to grab something. One moment, please. Okay. Now, sorry about that, team. Here I have a bucket of water that is spinning around in a circle like this. Let's say that it's spinning this way. And let's put some water here in my bucket. There's a little bit of water there. Here's a little bit of water here. Here's a little bit of water here. Here's a little bit of water here. Okay. Now here's the question. When I spin it fast, if I can spin it fast enough, then the water will actually stay in the bucket the whole way around, and the water will never splash out of the bucket. The question is, why is that true? Well, if you had a bucket of water, here's what you know. If you had a bucket of water like this, and you held that bucket of water straight above your head, and it wasn't spinning, well, then you would end up very wet because all of the water would fall down on you, and that would be quite an unhappy day unless you were looking for a shower. But for some reason, when it's moving, then all of a sudden the water stays in the bucket. And this has everything to do with inertia. Here's the idea. The water that's in this bucket has inertia that is going this way. Because it has inertia that is going this way when it gets up to the top, obviously. Here it has inertia going this way. Here it has inertia going this way. You get the idea. And again, we say inertia going. That's not really the best way of talking about the situation. It'd be better to say momentum going in a certain direction. But you could say that it has inertia and it's traveling this direction, and so it would like to keep on traveling that direction. Well, as this bucket of water is going, the water would like to keep on traveling this direction. Hey, if the water kept traveling this direction and it was under the influence of gravity, well, then it would follow some projectile motion path like this in a nice parabola. But here's the idea. If I swing this bucket fast enough in a tight enough circle, if I swing it fast enough, well, then do you see that the path of where the bucket is going dips underneath the parabola? So the water would like to go this way, but the bucket forces it to stay on this path. And so the water doesn't go, it's not as though the water wants to go straight down and it's forced to go straight down, or it's forced in when it's in the bucket. The idea is that the water would like to go in a parabola shape, but it's forced to go in a circle shape. And so instead of being able to go in the parabola shape that it wants to, it stays in the bucket here because the bucket will intercept its parabola. So instead of being up here where it wants to be, the bucket will keep it right here. That's kind of the first way of looking at this thing, is saying, well, because of inertia, it actually wants to make a parabola shape, but the circle keeps it underneath the parabola. Now, there are two ways that you can make sure that this happens, that your circle-y shape is tighter than your parabola so that the water is forced to stay on the circle, which means it has to stay in the bucket instead of going where it would like to go, which is in the parabola shape. One way to do it is to make your parabola bigger. The way that you do that is you swing your bucket faster. If you swing your bucket faster, well, then you know that will stretch out your nice parabola here, which I can't stretch out all the way because I run into this other thing. But it will stretch out your parabola here, and stretching out your parabola means, well, now it's definitely going to stay in the bucket because when it ends up over here, the bucket won't let it go in the parabola shape that it wants to. The bucket will force it to stay in that nice circle. And so then the water will most definitely stay in the bucket because the parabola arc is so big that the water can't fall out. If you swing it too slowly, then the parabola shape gets smaller. Let me show you what I mean. If you swing it too slowly and you only have a little bit of velocity in the x direction here like this, then your parabola will look much smaller. And then the water, that was a very bad parabola, but you get the idea. The water will fall out of the bucket, taking the path that inertia would have it take, and gravity, the combo of inertia and gravity would have it take, which is this nice parabolic arc here. So if you go too slow, then the water can go in the parabola that it wants to go. But if you go fast enough, then the water can't go in the parabola because the bucket stops it from going where it wants to go. And so the water will stay in the bucket if you go fast enough because going fast enough makes your parabola bigger than your circle. So that's one thing that you can do, is you can increase your speed. But there's another thing that you can do, and that's to decrease the radius of your circle. If your circle is smaller, well, then that parabola will definitely outstretch your circle, and so then you'll be able to stay. Have you noticed before? I want you to picture this in your head. If you're going on a roller coaster and you're trying to make it all the way around the loop, which loop is going to be easier to make it around without falling off? The loop that is big or the loop that's small and tight? A really tight loop will be easier to make it around without falling out, but a really big loop will be harder to make it around without falling out. This corresponds to our equation for centripetal force. Centripetal force is mass times velocity squared divided by r. And here's the other way, sorry, not velocity, this is your tangential speed. Here's the other way of looking at this problem. Basically, the idea is if you want to get this water to stay on the bucket, you need the water to press up. I'm going to change my color here. You want your water to press up against the base of the bucket as hard as possible. You don't want that water to go flying out. So the question is, how do we get that water to press up against the base? Well, here's the idea. If you can get the base to press up against the water, Newton's third law, then the water has to press up against the base. So just as hard as the base of the bucket is pressing the water, that's how hard the water will press up against the base. You increase that pressing force, and that water will stay in there because it's pressed up against the base, and the base is pressing up against it. Well, if you want to increase that pressing force, here's the idea. In this case, it is the normal force of the base of the bucket. Well, it's the normal force of the base of the bucket that is acting as a centripetal force. The water would like to go this way, but the normal force keeps it going in a circle. Then the water would like to go this way, but the normal force from the bucket keeps it going in a circle. The water would like to go this way, but the normal force from the bucket keeps it going in a circle. And so on and so forth, all the way around. It's the normal force that is pushing the water in the bucket down towards the center of the circle. And so it's the normal force that's going to act as the centripetal force here. So here's my idea. If I can increase the centripetal force, I can increase how hard the base of the bucket is pressing on the water, which increases how hard that water is pressing on the base of the bucket. Now, in order to increase that centripetal force, all that I have to do is I have to make it spin a lot faster, or I decrease the radius. If I make it spin way faster or I decrease the radius, then all of a sudden I'm asking it to go in a very, very difficult circle. If I ask it to go in a very easy circle, well, that would be something like, hey, here's what you're going to do. We're going to go nice and slow around this circle. Can you just gradually make a turn? If we go nice and slow around the circle, we make a very gradual turn. Well, that's not very hard, and the normal force doesn't have to be very big to make that happen. But if I say, hey, we're going to go in a circle and we're going to go really fast and you got to make a really tight turn right now. Right now is the time to turn. Hurry, turn, 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 turn. You don't have much time. We're going so fast that you don't have time to turn. Well, then, all of a sudden, that's a much harder circle to go in because your inertia would like to keep you going in a straight line. And I'm asking you to go in a circle and I'm asking you to accelerate very quickly because I'm asking you to change your direction very quickly if you're going very fast. So if I'm asking you to change your direction very quickly because you're going very fast, then that normal force is going to be huge because it takes a lot of force to keep you going in a circle. Think about it. The faster something is going, the more momentum it has going in that direction. So to demand it to go in a circle, to demand it to change its path, that's a big demand. And so it increases the normal force because the centripetal force has to be bigger in order to keep it going in a circle. If I increase the normal force by increasing the speed, then the bucket presses down on the water harder and the water presses up on the bucket harder. You can think of it as the water having more momentum. It has a bigger tendency to keep doing what it's doing, or you can think about it as the floor having more momentum. It has a bigger tendency to continue going in a nice straight line. Or you can think about it as that floor of the bucket is pressing harder on that water, so that water has to press harder up against that floor. The other thing that you could do is you could decrease the radius of the circle. If you decrease the radius of the circle, I want you to imagine, if I say, hey, you got to make a really, really tight turn versus a very big and very gradual turn, same thing. If you make a really tight turn, well, that's a much harder turn to make. And so making a much harder turn like that, well, that is going to be much more difficult. It's going to take a much bigger force to actually keep you in a smaller circle than it is to keep you in a big circle. Big circles are nice and easy. It doesn't take that much force to keep something going in a big circle. It takes a lot of force to keep something going in a very small circle. So you got a small circle, you decrease the size of your radius here. That increases your centripetal force required to keep it going in a circle, which increases your normal force. The water presses harder up against the floor of the bucket presses harder up against the water, and the water stays in the bucket. Those are two ways to think about the situation. We're going to do another practice problem here. I'm going to go ahead and pause this, and then we're going to go to another page here so that we can do a little bit of a practice problem, but I'm going to draw it first so that you can kind of see the situation. But as I get this pulled up, can you take a quick moment, think to yourself, can you explain why the water doesn't fall out of the bucket if it's moving, but why it does fall out of the bucket if it's not moving? Go ahead and tell yourself that. I'm going to pause it real quick and get another page queued up. One sec. Okay, see if you can catch this vision. Suppose that the year is 3025 and we have exhausted all of Earth's resources, and we decide that the time is now to go and move the entire human civilization into outer space, WALL-E style. Now, we learned a few lessons from WALL-E, a lot of lessons from WALL-E actually, and one of the lessons that we learned from WALL-E is that it's very important that people are able to walk. Now, here's the problem is that if we take a spaceship up into outer space and we're just floating around in outer space, well, then there's not a lot of gravity, which makes walking pretty difficult. So we need some way to simulate gravity. Now, here's the idea that we're going to use for simulating gravity today. If you have, I don't know if you've ever done this ride before, but there's a ride at Lakeside that used to be, oh gosh, wait, let's see if we could do this. I'm not quite ready for that layer yet. Let's make a new one. And see if this works for us. Okay, let's see. Good. Okay. So let's suppose, and I don't know if you've seen this ride before. I don't think it's been there in a while. Maybe it is still there. But there's this ride at Lakeside that is basically like a spaceship shaped sort of thing. It probably looks something sort of like this. And what you can do in this ride, the whole point of this ride, it has like all these cool lights on the outside, but it's mostly black. And you get on the inside, and what you do is you lean up against the wall like this. Here's my little stick figure leaning up against the wall. Yay! And everyone leans up against the walls like this. And then this thing just starts to spin like crazy. It spins super fast, around and around and around and around. And as it spins, it's crazy because what happens is as you're like sitting there and this thing is spinning, you actually feel like you get sucked to the wall. Now, someone who is not speaking correctly would say, well, there's a centrifugal force that pulls me towards the wall. But we know that that's not true. Really what's happening is that your inertia is trying to keep you going in a certain direction, but then the wall gets in the way. And so you keep trying to go in a certain direction, the wall gets in the way, and so you feel sucked to the wall. Are you really sucked to the wall? No. It's just that your inertia is pulling you, and even that is not really a great way of talking. But your inertia wants you to keep going in a certain direction, and the wall gets in the way of that, and so then the wall exerts a normal force on you like this. Now, if the wall is exerting a normal force on you and the wall is pressing on you, then you are also pressing up against the wall. That's Newton's third law. So you feel all pressed up against the wall. And what happens is you actually get so pressed up against the wall here that, sorry to erase this random person's legs, that's a little uncomfortable, but you get so pressed up against the wall that you could actually lift up your legs like this in the air, and you could still stay on the wall and you'll stay stuck there and you won't fall down. Why? Because the normal force is acting as a centripetal force, and that centripetal force is so big that you actually are pulled towards the wall more than gravity pulls you down, and then there's a force between the wall, which is friction, and so then that holds you up. But anyway, the main point is, imagine if we took this whole situation and we turned it sideways like this, and then we had something that was rotating like this way. This is a really bad picture. Let me draw it like this. Let me think about how to draw this. In class, I just kind of describe it and show it, but it's kind of hard for you to see. Imagine this. Imagine if instead of like going in circles around this way, what if you had, instead of like laying your back up against the wall like this, what if you could reposition yourself so that you had your feet up against the wall like this? Well, here's the idea. Inertia would try to keep your feet going out this way, but the wall would get in the way, and so your feet would feel sucked to the floor. Are they really being pulled down towards the floor? No, it's really just your inertia that you're experiencing. But your inertia would keep your feet grounded on the floor. The floor would push up against you with a normal force like this. Here's the idea. What if for our rotating space, or what if for our space colony in the year 3025? In the year 3025 for our rotating space colony, suppose that instead of making some fake gravity, the way that we make that fake gravity, I'm doing my words really badly right now, but what if instead of doing this, we make our spaceship look like a bike wheel? Imagine this. Imagine that this bike wheel is spinning so that everybody's inertia is pulling them outwards, but then the centripetal force, which is the normal force of the floor, is pushing them inwards. So that each person experiences, I'm going to do this here in this color, each person is going to experience a normal force. Oh gosh. Come on. Okay. So that each person is experiencing a normal force like this towards the center of our bike wheel spaceship. If that's true and every person is experiencing a normal force like this, well, people would say, I feel exactly the same way as I do when I'm on Earth. Because they would say, well, when I'm on Earth, then, let me draw somebody on Earth. They'd say, when I'm on Earth, then I feel gravity pulling my feet down to the floor. And then they would say, and I experience a normal force from the floor pushing me up. And here, if we could calibrate this thing so that it's spinning at exactly the right speed, we could get it so that their inertia makes it so that the normal force is exactly equal to the size of their weight. And if the normal force is exactly equal to the size of their weight, it'll feel just exactly the same way as it does when a person is standing on Earth. The question is, if we were to make this rotating space colony, what kind of radius would we need? Now, there are a few factors that we need to take into account. First, we can't have this thing spinning too fast or people will get ill. The Earth is spinning 1,000 miles an hour, but its angular speed, that's its tangential speed, its angular speed is 1 revolution per day, which is such a low revolution that really your body can handle that. However, on our space colony, we can't have way too many revolutions in a certain amount of time or people will start to get sick. So let's say something moderate, something that most people would be able to handle. Without getting ill. Let's say that we say that your angular speed is 1 revolution per minute. So you go around the whole circle 1 time every minute. Suppose that. Now, here's the key. If we're going to make this feel like Earth, we need the normal force to feel exactly like a person's weight. And the normal force we know is a centripetal force in this case because it's what's keeping those people going in a circle. Their inertia would have them go flying, but the normal force keeps them going in a circle, so it's acting as a centripetal force. We know that the strength of the centripetal force is mvt squared over r. And we know that Fg, a person's weight, would equal mg on Earth. This is someone's weight on Earth. It's how much weight we want them to feel like they have, or how hard we want the normal force to be pressing up on them. Now, a lot of students would say, okay, fantastic, now let's rearrange and solve for r, but here's the problem. There's actually a secret r that is hidden inside of this velocity equation. Take a look. If you got tangential speed here, well, that's going to be 2 pi r, there it is, all over t. So once we expose that r here, now we might be able to rearrange, except that this t here is not given to us. We have omega, but we don't have t. Now, in order to find the period of motion, we can rely on our equations for omega. We say that omega is 1 revolution per the amount of time it takes to go in 1 revolution, which means that the period would be how much would be 1 over, basically, you can do it this way, 1 over omega, which means that it would be 1 minute per 1 revolution, Or if we want things in good SI units, we would say it's 60 seconds for one big circle. So now we can take a look here. Let's do some rearranging work. We got m times 4 pi r squared divided by t squared times r. You'll notice that one of our r's will cancel out because we got 2 in the numerator and 1 in the denominator, equals mg. And notice this, my m's cancel out, so I'm left with an expression for g that looks like this. G is equal to 4 pi r all over t squared. Now this is the part where some students say, wait a second, Miss Wilson, you're saying that g depends on the radius of your spaceship and the period of the spaceship? Remember, we're not talking about real g here. This is fake gravity. This is gravity that we're inventing. Now we can still invent gravity so that g is whatever we want it to be, but g really deep down represents the centripetal acceleration of each person. So we're trying to make the centripetal acceleration of every person equal to g. That's the ultimate goal. Now if we rearrange for r, we get that r is equal to g times t squared. Oh my GOSH, I forgot to square my pi. Oh gosh, classic mistake on my end, really. Okay, there we go. That looks so much better. Divided by 4 pi squared. That's a terrible pi. Oh gosh. Okay. There we go. Now we could plug in numbers, and if we plug in numbers, we plug in for g what we want the centripetal acceleration to be. We want the centripetal acceleration to be 9.81 meters per second squared. For t, we can plug in, I'm right on the edge here, 60 seconds squared. Divide by 4 pi squared. Plug that into your calculator, and you would get that we need the radius of this guy to be 859 meters, which is quite a few meters, until you consider that we're trying to fit the entire population of Earth on this rotating spaceship, and then you're going to start to think, well, maybe we need something bigger than 895 meters. Suppose that we get this whole thing set up, and then we have one character, one human who comes along and says, hey, love the idea, but I'm going to need my own private suite. And so this person says, I'm going to need a private suite that extends off the edge here of this spaceship. Sorry, I'm going to erase my little guy here who's showing us that the normal force wants to be equal to the weight, because that's what's true on Earth. And so we're creating fake gravity so that the normal force is the same size as what your weight would be on Earth. Okay. Suppose that someone says, hey, love the idea, I'm going to need a private suite. And so they say, I'm going to need a private suite that kind of extends off the end of the spaceship right here. Like this. Oh gosh, wait, let's go a little bit smaller here. Okay, so someone says, I'm going to need a private suite over here. Thank you very much. I do consider myself to be a person of supreme importance. Most likely her name would be Karen. So Karen is over here, and Karen says, I need my own private suite. And suppose that Karen's private suite is a distance 2r away from the center of our rotating space colony. Here's a question for you. If Karen is in her private suite 2r away from the center of the rotating space colony, then what would Karen say that her weight feels like? Would she say, my weight feels like it's more than usual? Would she say, my weight feels like it's equal to usual? Or would she say, my weight feels like it's less than usual? Now remember, what her weight feels like to her is going to be how hard the ground is pressing up on her, how big that centripetal force is. So when we look at this equation here, we would say, well, her R just increased, so that just means that her weight that she feels would go down. But wait, because that's not true. Because if she's in her private suite out here, not only did she increase her radius, she also increased her tangential speed. And notice, tangential speed matters more than the radius does. When we go all the way down to g over here, you'll see that g is equal to 4 pi squared times r over t squared, which means if she doubles the radius, she'll double her value of g that she experiences and feels. And so when she's double the radius out here, she would double her sense of g, and so she would say that she feels twice as heavy out here as she would inside the as everybody else who's in here in the rotating space colony. Okay, Now, one last question that we are going to try together. This one actually comes from your textbook. This is from page, let's see here, 238. Okay, this is textbook page 238. We're going to do question number 4 together. Here's what it says. Allow me to flip. Flip, 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 flip. Oh no, I was almost there, and then I went past it. Flip, 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 flip. Okay, that's too far. Too far. Go back. Go back. Page 238. I'm almost there. Okay, that's 37. Yes. Okay, here's what it says. It says, a 905 kilogram car travels around a circular track with a circumference of 3.25 kilometers. If the magnitude of the centripetal force is 2,140 newtons, what is the car's tangential speed? Okay, let's start by looking at what we have here. We have a car. I'm going to draw a nice, over-the-top view. We have a car that is going around a track. Here's a track. You can tell it's completely and totally different from our spaceship. Let's see if I can do it. Oh no, I can't do it. Oh, this is so very hard. Ugh. Oh, it's terrible. Okay, sorry, I'm trying one more time and then I swear I won't try any more times. Whatever this looks like, that's just gonna be what we go with. Okay, here we go. Making a circle around a circle. It's actually really hard when you can't see what your pen is doing. Okay, yes, here we go. We got a race car. Nope, just a regular car. Okay, we got a car. And that car is traveling here around this track, like this. And the question is, what is its tangential speed? And it tells us a few things about this car. It says this car has a mass of 905 kilograms. It also says that the circumference of this track, which I shall label capital C, the circumference of this track is 3.25 kilometers. Wow, that took me way too long to find. Which, when I translate it to meters, which I will, is 3,250 or 250 meters. Here, I moved that decimal place over 3 times. And then it tells us that the centripetal force here that this car is going to experience, which is most likely the force of friction between the tires and the road, that centripetal force here is going to be 2,140 newtons. And it asks us, what is the tangential speed of the car? Now, here's how I would go about doing this problem. I would start by saying, whoa, did I give this? I meant to say C for centripetal force. That is awkward. Okay, I would start by saying that my centripetal force is equal to mvt squared over r, like so. Then I say I'm looking for my tangential speed, so I can rearrange. I get F times C, not F times C, F sub C times R divided by M, square root both sides, square root both sides, like so. Now here's the only problem. I have the centripetal force, I have the mass of the car, but I was not given the radius. Instead, I was given the circumference. Here's what I know is that the circumference of a circle is equal to 2 pi r. And so if I want to know r, I can just take r is equal to c divided by 2 pi. Now I can plug this guy back into this other equation here, and I get fc times the circumference divided by 2 pi m. Next, I can plug in numbers. When I plug in numbers for my centripetal force, I plug in 2,140 newtons. For the circumference, I can plug in 3,250 meters. For my mass here, I can plug in 2 pi times 905 kilograms, square root, top and bottom, and that gives us for a final answer 35.0 meters per second. So there you go. Now, we talked about a lot of things today, so a quick overview. We started by talking about centripetal force, and we said, hey, any type of force that causes an object to go in a circle, that is a centripetal force. So you can have lots of different, oh gosh, wait, that's not the one that I wanted. Oh, that's so awkward. Don't look, that's from last time. That's embarrassing. So we talked about how lots of things can be centripetal forces. Gravity can be a centripetal force. The tension in a string can be a centripetal force. Friction between tires in a road can be a centripetal force. It's really any kind of thing that causes something to go in a circle can be a centripetal force. Here in this example, we saw the normal force acting as a centripetal force. And that's the normal force between the passenger who is pressing up against the side of that car. That creates a centripetal force so that even though their inertia is going this way, the force from the car door pushes them back this way, and they're able to make the turn even though their inertia would have them keep going. In fact, it's always the case that it takes a combination of inertia and a centripetal force in order to make a circle. You have to have inertia, which wants you to keep going, and a centripetal force, which pulls you back towards the center of the circle. That is a terrible ice cream cone. Now, we also talked about how the centrifugal force is not a real force. The centrifugal force is just a way of describing the feeling that you get from inertia. We talked about the bucket of water trick and how the bucket of water trick works by basically making this water want to go in a parabolic shape, but then the bucket intercepts the parabolic shape so that the water can't go where it actually has to go. Instead, it gets stuck in the bucket. The normal force of the bucket is what acts as a centripetal force. In this case, if you want to increase that centripetal force and increase the normal force, get the water to stay in the bucket even better, you can increase the speed or you can decrease the radius. Then we talked a little bit conceptually here and also mathematically about creating this rotating space colony where we have fake gravity, and that gravity isn't real gravity, it's just that the normal force is pressing up against the people inside just as strongly as gravity pulls them down, which is what happens on Earth, is that the normal force presses up on you just as strong as your weight pulls you down, and so that's why it feels the same. We said that then the normal force would actually be equal to the centripetal force because it's the force that's pulling the people towards the center of the circle, and that would equal mg if it was trying to match their weight on Earth. And then we talked about how if you were in something that was further out, your weight would actually, your apparent weight, which is not really your weight, what we're really talking about here is the normal force of the floor pushing up on you, but the normal force of the floor pushing up on you would be more than it would be if you were in the center because you have to take into account both V, T, and R. And then lastly, wow, this is a very, very long overview, but a lot of concepts covered today. Lastly, we talked about how if you had an example here, and we did a little mathematical example, we had to take care of our circumference here in order to find the radius. And so you can see that we're going to have a lot of different examples here where you're going to have to combine multiple equations or use things like geometry in order to do the problem. And wow, that was everything. I do hope that you have just a wonderful, wonderful rest of your day. Bye, good people.